Hello class, welcome to problem solving of chapter number 3 of the Business 2400, the decision modeling. In this video, we will go through some questions and problems available in your course content. The questions are based on two files, the problem set T3 and the textbook problem of chapter 3, which are available in the Brightspace course content. So let's start with question number 2 of the T3 file, which is an ingredient mix and blending problem. In this question, we have an oil refinery which produces two types of outputs or final materials, final products, based on three types of inputs. So we have three inputs, we mix them together, and we produce two different products. Each input and output has different characteristics. For example, input number 1, we buy it for 42 cents, and the sulfur percentage of it is 2.2. We mean that in 100 kilograms of input number 1, we will have 2.2 kilograms of sulfur, and its thermal value is 15,000 kilojoules per liter. And the same for the other inputs. For example, regarding the output number 1, we sell it for 63 cents per liter, and its sulfur percentage should not exceed 1.2, and its thermal value should at least be 16,000 kilojoules per liter. The process has some limitations, and it is not like that we can have as much as input or output we are willing. It has an operation capacity, it has some limitations for the amount of output and input, and maybe the most complicated constraint for this problem is how to present the blending characteristics of the output based on the inputs. So let's use a simple example to show how should we handle this special constraint. Very simple example. Assume that we have two types of materials we are willing to mix. We will consider two cases for this. In the first case, we use all of the inputs to produce the output. I mean that all of input number 1 and all of input number 2 will be mixed together to produce the final product. The amount of input number 1 is 100 liter, and 50% of it is water. The input number 2 is 200 liters, and 60% of it is water. So the question is, how much water we will have in the final product by mixing these two inputs together? Very simple calculation. The 50% of input number 1 is 50 liters, and 60% of input number 2 is 120 liters. So totally, 170 liters of the output will be water. In the second case, I am not using all of input number 1 and input number 2 to produce the final product. Only 30% of input number 1 and 70% of input number 2 will be used for this purpose. The constituent water of this element, I mean input number 1, is 50%. So totally, 50 liters of water will be transferred to final product from element number 1. A very simple multiplication here. And following the same process for element number 2, we will have 84 liters of water being transferred from input number 2 to output, and adding these two numbers together, I will get a total number of 99 liters of water in output. So two things are important here: the total amount of each input and the portion of each input being mixed to produce the output. So this logic will help us to handle the mixing characteristic of this problem. So again, 90 liters of water in output, as you can see. Let's assume the question. So what I suggest you to do is first try to understand the problem and simplify it. You can use diagrams, you can use figures to see what exactly goes on there and what is the relationship between different parts of the problem. So as you can see in this figures that I have provided for you, I have different inputs there, the output there, the blending process there, and based on the explanations that I provided you in the previous slides, you can see those relations, the portions, the amount of liter that we use from input number 1 to output number 1, and from input number 1 to output number 2, and so on. So what am I going to do is to define my decision variables as follows. I should have a number of liters of each input, which we will show with I, the number of liters of each output that we will show it by O, and the number of liters of input I, which is used in producing output J, which is shown by X, indexed by IJ. So first, let's see what is my objective function should be. Well, I have the selling price, I have the buying price, so it is logical to focus on a profit type objective function. So we are willing to maximize our profit, and for that purpose, we should have these costs and we should have the benefits. What I get from selling output number 1 is 63 cents. So 63 cents of each output. Sorry, for 63% of output number 1 for each liter of output number 1, and 91 cents for selling each liter of output number 2. And what is the price for buying each liter of input number 1? It is 42 cents. What is the buying price of each input number 2? It is 76 cents. And what is the price for buying each liter of input number 3? It is 60 cents. So this is how I form my objective function. Let's go for the constraints that I have in this problem. As we discussed before, the amount of sulfur in each output should not exceed a certain amount. For the output number 1, it shouldn't exceed 1.2% of the whole product. So how we show it is exactly the same way we use in our example of 2 inputs and 1 output. Based on that, we will have 2.2 x11. This will show the amount of input number 1 being used in output number 1. And then I should have the amount of input number 2 being used in output number 1. And then I should have the amount of input number 3 being used in output number 1. The summation of these 3 elements should not exceed the whole amount of sulfur in the output number 1. The second constraint is the same as this one. And then we will have the thermal value, which is of minimum type. So each output should at least have a certain amount. For output number 1, we should have at least 60,000 kilojoules per liter. And for output number 2, we should have a minimum amount of 18,000 kilojoules per liter. This is shown in constraints number 3 and constraints number 4. The other constraint is the capacity. The capacity of the refinery for each of the inputs is 500,000 liters. So refinery can't process more than this amount. So we will have 3 separate constraints to show each input's maximum amount. And for the outputs, the refinery can't handle more than a specific amount, which is shown in output number 1 limit and output number 2 limit. And if you look at the diagrams, you look at the diagrams, you will see that the total amount of input number 1 is based on 2 separate amounts, which is the amount being transferred or being used in output number 1 and the amount that is being used in output number 2. So I should have a balance constraint here for each of these inputs. So I1 equals to x11 plus x12, and the same for the other 2 inputs. And also, following the same logic, the total amount of output number 1 is based on those 3 inputs. So O1 should equal to the amount of input number 1 being used in output number 1, plus the amount of input number 2 being used in output number 1, and the amount of input 3 being used in output number 1. And the same logic for the second output or the second product. And all of our variables are non-negative. I can't have negative values of any of them.